Okay, so in this video lecture, um, we're gonna go and we're gonna pick up in 5.4. We started at a little bit. First we reviewed not reviewed, but went over rational functions and asymptotes, talked about limits. Because we're gonna need those ideas when talking about the graphs of tangent, tangent, cotangent, secant and the cosecant graphs. These graphs are going to have asymptotes, and that's because they are defined as ratios of trig functions. So you have places where you could have division by zero, and as we saw, division by zero can be places where you have vertical asymptotes. All right, so let me share my screen. I'm gonna work from the book since there's a lot of diagrams and graphs. I'm just gonna work through the book, like read through it with you. Maybe take some notes in the book. All right, let's see. Share screen. All right, so hopefully you can see what I'm seeing. So last time we looked at why this. So okay, so another thing we talked about was um another thing we spoke about were periodic functions, functions that repeat. Their values repeat. And that was reflected in the fact that the graphs repeat. They have the same pattern over some interval. And we saw a while back that sine and cosine have a period of 2 pi right here. So the sine and cosine have a period of 2 pi. And then last class we saw that this tangent has a period of pi, and the same thing with cosine, the cotangent. Now, because cosecant is just well, actually not write it like that. Because the cosecant of x is equal to 1 over sine x, and the secant of x is equal to 1 over cosine x, it's pretty easy to see that these actually have period of 2 pi. So the and that follows immediately from the fact that the cosine and the sine have a period of 2 pi. But the tangent and the cotangent they're the kind of the odd ones out. They have this period of pi. And we looked at a derivation of that. So what that means really is that when we want to determine the graph of tangent, which is the whole point of this section. So this is to just remind you, this is 5.4. We're looking at the graphs of the rest of the trigonometric functions. We want to this is going to simplify our lives basically. The fact that this function is periodic, it means we only have to graph the function over a interval of length pi, as it says here in the book. We only need to graph. We only need to sketch the graph over an interval of length pi. Now, recall that tan of x is defined as, or one way of thinking about it. There's lots of different ways of thinking about these trig functions, but one helpful way is to think about it in this way, is that the tangent function is sine over cosine. So what that means is that we can have the graph of tangent has vertical asymptotes wherever cosine of x is 0, right? That will give us division by 0. As we saw that when you have a rational function or a function that's a fraction of two functions like tangent of x, wherever you could possibly have division by 0, that's where you're going to have a vertical asymptote. Remember, vertical asymptote is a vertical line which the graph gets arbitrarily close to. Possibly it could pass through the vertical asymptote. We saw examples of that, but it basically has to like stay fixed to this line. It gets very close and it like hovers around it, or it could hover around it. So for example, we can have this equation, cosine x is equal to 0 when x is equal to plus or minus pi over 2. Um, and that's because if you do your unit circle business, pi over 2 is this point right here. It corresponds to pi over 2 is right here. So coordinates are 0, 1. And remember, the cosine just gives you back your x coordinate, and then this would be negative pi over 2, and the corresponding point would be 0, negative 1. Again, cosine of a arc length, or really these are angles actually. These pi values, pi over 2, negative pi over 2, these are really angles also. So the cosine of an angle or an arc length is your x coordinate, and you can see in both cases this is 0. So this equation is satisfied when x is, for example, either one of these values. This is, of course, there are a lot more values for which this equation holds. There are infinitely many, but we only really care about these ones for our purposes. And so because we get division by 0 here, because cosine of x is 0 at these points, that's where we could get division by 0 if we tried to plug in those values into the tangent function. So we're going to have vertical asymptotes here. The function is going to go off to infinity in some way. It's going to blow up. So they make this table right here, and I guess they're using a calculator. So I just want to know. So yeah, we're going to make a table of values of tangent x, where x is close to pi over 2, and they know here a decimal approximation of pi over 2 is this. So we're gonna make a table. They make this table here, and I'm guessing they're using a calculator. And they're gonna take values of x, which are getting closer and closer and closer to pi over 2. So you notice, like, so we have 0, pi over 6, pi over 4, pi over 3, and then we have 1.4. That's close to 1.5. That's close to this decimal approximation right here. And then you take 1.5, 1.55, 1.57, 1.5, and you can imagine that this table just keeps going down, and then you're plugging these values in to tangent x. So you plug 0 into tangent x, you get 0, pi over 6, you get 0.58, etc. And notice as x gets closer and closer to pi over 2, notice what is happening to these values. They're getting larger. So we have 0, 0.5, 1, 1, 5, 14, 48, 1,255, 10,000, etc. These values are going off to, so as you go down, as you get closer to pi over 2, you're getting closer to x, the tangent of x is going off to infinity. So that's one way to see it. Another way to see it is another way to see why. So here they summarize this table right here. Remember this notation. Um, so they say as x approaches pi over 2 from the left, tangent x goes off to infinity. And you can kind of write this a little more concisely, as saying that the limit, let me actually not put it there. The limit as x goes to pi over 2 from the left of tangent x is equal to infinity. And I should know, actually, I didn't say this. Because so yeah, so this right here is just shorthand for this, and this right here is shorthand for what this table expressed. So remember, limits aren't scary. They're just it's a very basic idea to express something pretty intuitive. Um, so you so let me back up a little bit though, because I realized I didn't explain something. So yeah, because this function has a period of pi, as we noted here, we only need to sketch a graph. We only need to sketch the graph on any interval of length pi. And then as they note, well, since pi over tan of pi over 2 and tan of negative pi over 2 aren't defined, they are not defined. It makes sense to graph um it makes sense to graph tangent up to those points. So we're gonna actually, as we say here, we're gonna sketch the graph on this interval right here. And notice this does have a length of pi, right? What's the length of this interval? So the length of the interval negative pi over 2 to pi over 2. What's the length? You just take the difference in the endpoints. So pi over 2 minus pi over 2. So it's going to give you, well, you can see it's when you add these, it's going to give you pi. So the length of this interval is in fact pi. So this is a good interval to graph tangent over because it's gonna capture the whole behavior, and then by periodicity of this function, you just the pattern repeats. Okay, so this table tells us that when we take the limit of the tangent of x, let me make this a little bit neater. Tangent of x as x approaches pi from the left, pi over 2 from the left, you get infinity. And another way to see this is to, again, use the definition of tangent right here. So let me see. Okay, so I got some room here. So remember, tangent of x is sine over cosine. So this is not going to be very rigorous, but it's going to give us some idea as to why this limit is true. So what happened? So um, for this, you need to remember how these sine and cosine are defined. So what is happening as x approaches pi over 2 to sine? Well, we know actually that it's going to be 1, right? Because we can actually just plug in pi over 2 to sine of x. Um, or you can make a table again. You can make a table of values, and you'll see that when x gets closer and closer to pi over 2, sine of x gets closer to 1. And as for cosine, this is let me actually pull up OneNote and make it easier. All right, so let's think about another reason why the limit as x approaches pi over 2 from the left, why does this go off to infinity? So on the one hand, we saw from the table, you can just literally plug it into a calculator and see, oh yeah, these values, as you take x's closer and closer to pi over 2, you get, and you look at tangent of those values, you get numbers that go off to infinity. But we can see this without using the table, by again using the definition. So we get cosine x, sine of x over cosine x. And so let's draw a circle, and the value we're approaching is right here. This is going to be pi over 2, and it corresponds to the point 0, 1. All right. So what does it mean to take x as a let's actually use t just to, so we don't get confused by talking about x coordinates and evaluating tangent at x. So let's use t. And remember, these are just variables. It does not matter. All right. So we're taking I want to make sure I get this right. So we're gonna take, yeah. Anyways, so okay, so this is how it's gonna work. Okay, so this is our reference point. It's t value of 0, and it corresponds to 1, 0. Now what we're gonna do is we're gonna imagine ourselves marching along and getting arbitrarily close to this point right here, to t equals pi over 2, but not actually touching it. So we're gonna get our, oh, I did not mean to do that. Let's see, can I redo this? Okay. So we're gonna get arbitrarily close to this number right here, but not actually touch it. So let's evaluate the limits of these two functions individually. Well, you can see that like if I take this point right here and I look at the x coordinate, it's pretty big, right? It's close to 1, right? But then if I go up here and I look at the x coordinate, it's getting smaller. It's getting closer towards the origin. And finally, if I get like say to here and I look at the x coordinate, it lands right here. These numbers are getting smaller and smaller and smaller, the x coordinates. So what that shows you is that the limit as of pi over the limit of cosine of t as t approaches pi over 2 is going to be 0. These numbers are getting smaller. So and then for sorry, it's not undoing. As for the limit as t approaches pi over 2 of sine of t, you're going to get 1 because if you look at now, take these same points right here, this point right here. Let me use a different color now. So this point, and this point, these points are getting close to this point. When you like look at the y coordinates right here, they're getting closer to 1, right? So that's why this limit equals 1, and that's why the other limit is 0. So what should happen when we take the limit of t, the limit as t goes to pi over 2 from the left of tangent of x t? Well, that's the limit. By definition, tangent is sine of t over cosine of t, right? And we're taking t to go to pi over 2 from the left. Well, let's think about this now. So when we take this limit of this fraction, the sine of t is approaching 1, and the cosine of t is just approaching 0. So in other words, and then you're taking this fraction, right? You're computing the division. So what you're doing is you're taking something that's almost 1 and dividing it by some number that's almost 0, that's close to 0, right? But we know if you take 1 and divide it by a very a very small number, like 0.1, So if you take 1 and divide it by 0.01, you get 10. If you take 1 and divide it by 0.01, you get 100. If you take 1 and divide it by 0.001, you get 1,000. So these numbers are getting bigger and bigger and bigger when you compute this fraction. So that's why this goes off to infinity, because the sine of t is approaching 1 and the cosine of t is approaching 0. So you're taking 1 over, what you're doing is when you take this limit is you're computing these fractions where the numerator is basically 1, but the denominator is a very small number. So when you have 1 divided by a very small number, you get a very large number. So the limit is going to be a very large number. That is, the limit's going to be infinity. So that's another reason why this limit goes off to infinity. All right. And the same sort of reasoning justifies you can use to justify this right here. Oops. This right here. And again, this can be expressed by saying that the limit as x, I'm using x now, but x, you can use x or t, it does not matter. X goes to negative pi over 2 from the right of tangent of x goes to negative infinity. So let's look at this graph and try to figure out why is this the graph. So we're going to just look at this one for now, tangent. So we have our vertical asymptote here, pi over 2. So we have this pi over 2. And then we have this vertical asymptote over here, negative pi over 2. And we know what the graph should look like when you get really close to it, right? So when you approach, based on these calculations here, this one right here, and this one right here, which I justified for you using this table and using the limit calculation in the OneNote document. So what this says is that when you approach pi over 2 from the left, you should go off to infinity. And that's what we see. This graph is going off to infinity. In this case, the graph can't go through pi over 2. So we get arbitrarily close, but it will never actually touch it. And when x approaches negative pi over 2 from the left, you're marching along, or from the right, this function is going down to infinity, negative infinity. And now, um, we know that from and we can actually work out the rest of the shape by computing some values here, right? So we know that tangent of 0. So this, I'm just going to write these down. I'm not going to go through the steps. You can go through the steps, draw your unit circle and figure out what these values are. But we know that tangent of 0 is 0. That's why we're going through the origin right there. We know that tangent of pi over 6 is I think that's what is that? Uh √3 over 2, maybe. I'm actually not remembering myself. Um so let's see. Maybe I had to write the table down actually. Pi over 6. Um Wait, that one should be 1, right? Pi over 4 should be 1. Yeah. So that one's easy to figure out. Tangent of pi over 4 is 1. And then tangent of pi over 6 should be, let's see, so it's going to be cosine of pi over 6, and that is going to be √3 over 2, I think. And then cosine is 1/2. That doesn't seem right, actually. Let me consult the unit circle. This, you, yeah, definitely remember the unit circle. You're going to need to remember the unit circle. So, oh, okay, I got it backwards. I just got it backwards. So the tangent of pi over 6 is actually, it's going to be 1/2 over √3 over 2, and then that simplifies to 1 over √3. So this is like less than 1, right? √3 over, so tangent of pi over 6 is less than 1, and that's what you see in this graph. Tangent of pi over 4 is actually equal to 1, and then tangent of pi over 3, that is going to be actually √3, I believe. Tangent of pi over 3, that's going to be √3 over 2 over 1/2. 1/2's cancel, you get your √3. And so, yeah, pi over 3 is just a bit bigger than 1. So that's why it's above 1 right there. So you don't actually need to evaluate these at a bunch of values. You can kind of figure out what they are from your basic, the basic ones we worked out. Pi over 6, pi over 4, pi over 3. And then you have their negatives over here. And so it's increasing. It's increasing like that, and it has to increase off to infinity. And then now it's decreasing over here, and it has to decrease to infinity. So this general shape can be worked out very easily by calculating at these 3 basic angles and 0, and their negatives, of course. All right. Yeah, and I'm gonna just say the same thing the book is saying. You can figure out, so the tangent, the function, in this case, you're going to actually plot it over the intervals 0 to pi. And the reason why is this. So cotangent is, tangent is sine over cosine. Cotangent is cosine over sine. It's the reciprocal of tangent. And this is, you're going to have vertical asymptotes where sine of x equals 0. And so, for example, it is 0 at x equals pi. And so you need to graph the cotangent over interval of length pi, and there's an asymptote at x equals pi. Also, x equals 0. So it makes sense to just graph it over the interval 0 to pi, like we did right here. So we're gonna graph from 0 to pi over 2. And doing the similar analysis, you can figure out why it has this asymptotic behavior like this. Basically doing the same thing and then calculating at a bunch of different angles. This will be the general shape. and it's going to repeat. It's going to repeat. This is just over the one interval. This shape is going to repeat, going to the left and to the right. All right. So yeah, I actually didn't need to erase that, but whatever. All right, so let's see what's next. Let's see. As they note here, the cotangent is undefined. It's not defined at multiples of pi. So you're gonna have asymptotes at all the numbers of that form right there of n times pi. All right. I'm gonna just save time. I'm gonna skip over this, but you can just do the exact same analysis to figure out what these graphs are. So yeah, you're gonna have for cosecant, you're gonna have asymptotes wherever sine of x is 0. Secant, you're gonna have the vertical asymptotes whenever cosine of x is 0. So, and you want to graph cosecant over interval 0 to 2 pi, which is what they did right here. So this is one period of cosecant x, and you're gonna have um so sine of x is 0 at, for example, pi. It's 0 at 0, and it's sorry, yeah, sine of x is 0 when x is 0, x is pi, and x is 2 pi. So you're gonna have these asymptotes at these points. The blue graph is sine of x, and the red graph is cosecant of x. And it's a more annoying. You have to go through more detail. You have to go through more cases. So like to figure out the asymptotic behavior. So for example, for this number right here, pi, you have to take a limit of this function right here as you approach pi from the left, and you'll see if you do the calculation, it goes off to infinity, and you have to approach this number pi from the right, and if you do that, you'll see it goes off to negative infinity. And then you can work out the rest. So you got to do left and right hand limits at pi. So kind of annoying. Same thing with the pi over 2 and 3 pi over 2, which is where cosine of x is 0. And hence you have, so cosine of x is 0 at pi over 2 and 3 pi over 2. And hence that's where the secant function has gonna have um vertical asymptotes. All right. Let's see what else. So and you can go through this. I'll let you go through that. So here's tangent plotted over more intervals. So we just plotted tangent from this point right here to this point, but you can see it just repeats, and we didn't go through all the details, but we saw the graph of cotangent plotted at this from this point to this point, but the shape just repeats. And we saw cosecant plotted from this point to like I guess right. Oh no, that doesn't make sense actually. But anyways, yeah. We saw from 0 to 2 pi on both cases. They didn't mark 2 pi on here. I don't know why. That's kind of stupid, but 2 pi should be like over here. And so this is gonna go down like that. And then this is gonna go up. So that's kind of how you complete the rest. But it just repeats. I don't think I'm gonna do a whole lot with cosecant and secant. Um, I don't think anything like that's gonna be on the final exam. If it does, I will definitely go over it then. But we were trying to cram in a lot of material, so I'm just gonna try to like pick and choose based on what I think is gonna be on the final. And of course, if there's something that we didn't cover that's on the final on the reading day, I'll use that to like go over any topics that um we didn't get to cover. All right, so let's see now. All right, so yeah, you can look at, now that you know the basic graphs of tangent and cotangent, and then the other ones, secant and cosecant. You can look at transformations, which is basically everything we've been doing so far. So, and this is why I wanted to use the book because these are kind of hard to graph. Their difference, that is. So you have 2 tangent x. So that's a vertical stretch, right? So it's gonna go, it's gonna, when you do that, it's gonna look like the red graph right here. Should be the, yeah. So the red graph is the plot of 2 tangent x. So you can see it's a vertical stretch. It stretches upward a little bit. Still goes through the same points on the x-axis, has the same x-intercepts. As for this one, when you multiply by negative, that has the effect of reflecting over the x-axis. So it's a reflection over the x-axis. Almost looks like a reflect. Oh, that makes sense actually. Um, so it turns out that remember tangent is an odd function, or is this even? Forgetting that. It satisfies this property. So what does that mean? It means that when you do this negative x, it means when you reflect over the y-axis, it's the same thing as reflecting over the x-axis. So that's why if you look at the graph of negative tan x, it looks like the same thing as this one right here. So you can either reflect over the x-axis or y-axis, you're going to get this same result. That's essentially what this equation is saying. And I think that I'm pretty certain that that is odd. That is when it means to be odd, an odd function, when it satisfies that equation for all x in the domain. Okay, so that's those graphs. And let's see what else. Oh, so now you want to talk about general cotangent and tangent curves. So you have this A factor, that's the amplitude. The K factor is going to kind of change the frequency or the period. The period and frequency are pretty related though. So now what this says is, so you, if I give you these general curves right here, we want to work out what is, well, amplitude doesn't really make sense in this case, right? Because it doesn't, amplitude means like you go up and then you max out and then you go down and then you min out. So it's like you're bounded. But these functions are definitely not bounded, right? But these still give you the factor of A, although it's not an amplitude, it's a stretch factor. So that will be a stretch factor. So but if I give you a general function like this with a t kx, what is going to be the period? Well, we know that the period of tangent and cotangent is pi, it's just pi. Now, what that means then is that as kx, so to complete one period, kx needs to vary between 0 and pi. That is, the graph of this equation is going to complete one period and then repeat if kx is in this interval. But you can just divide by k, right? And so that will tell you that you complete a period when x varies between 0 and pi over k. So this graph completes a period when kx varies from 0 and pi, but that's equivalent to x varying from 0 to pi over k. So that means that the period of this is pi over k. So here's that fact stated more generally. And then you can, it says that you, to graph a period, if you want to graph, and this, I should say the same discussion applies to this function as well, but cotangent. But I'm just going to mention the tangent. So same exact discussion applies to that. Here's the difference though. When you want to actually plot this function, the best interval, I mean, you can use any interval you want as long as the length is pi over k. But the best way to do it is just to use an interval of this form. It's centered at 0, right? 0 is in this interval. Um, so just take the interval centered at 0, and then for this one, it's best to just take the interval from 0 to pi over k. Just like you when if you didn't have this a and you didn't have this k here, it was just cotangent x, you take the interval from 0 to pi. So just a slight modification. So if you graph it over that interval, you'll get the whole behavior of the function, and then you just repeat that pattern. All right, let's see what else is left in this. I don't know if I want to go through a whole, yeah. Um, I'm not gonna, I encourage you to read this. Um, yeah, you should definitely read this, but just for the sake of time, it's because it's the same. So this discussion right here, let's see, is on the cosecant and the secant. It's the same exact kind of idea. So as once you know how it works for the tangent and the cotangent, the same sort of principles apply here. So I guess we'll just look at these last two examples. So yeah, we want to graph y is equal to tangent x, tangent to 2x. So the 2 is going to change the period. It's going to also what it means is it's going to correspond to a horizontal shrink, right? It's going to shrink it. So the period is, remember, it's sorry, is going to be pi divided by k, and then k in this case is 2, so pi over 2. The period is of this thing right here is pi over 2, and so using this kind of formula right here, um, k is equal to 2, you get negative pi over 4 to pi over 4. So we're going to graph it. The best way to graph this is over pi over 4. Now note, these are going to be points where this function right here is not defined. Why? If you plug in pi over 4, say, you get 2 times pi over 4. The 2 cancels with the 2 in the denominator, so you get tangent of pi over 2. And we know that that is undefined. We know that tangent is not defined at pi over 2. And then, so we have an asymptote at pi over 4, and the same reasoning tells us that we have an asymptote at negative pi over 4. All right, so um, yeah, so the graph is going to have the same shape as the tangent function, but it is shrunk, as I said, horizontally by a factor of 1/2. So, yeah, it's hard to even tell the difference, honestly. It looks the exact same, right? Um, but notice, I don't know if I can actually, let's see. I guess I can just scroll up. So here's the graph of y is equal to tan 2x. Same general shape, but now notice, instead of plotting from pi over 2 to pi over 2, and notice that's where we used to have asymptotes, vertical asymptotes. We're really just gonna plot it over pi over negative pi over 4 to pi over 4. And it's gonna have the same exact shape. It's gonna be compressed, in other words. And then the pattern repeats. So now we no longer have asymptotes at negative pi over 2 and pi over 2. For this other one, oh yeah, so notice this other graph, it's just you're shifting by pi over 4. So as it says, the graph is the same as in part A, but you shift to the right pi over 4 units. So now the origin to figure out what the graph to figure out how a horizontal shift works, remember you're subtracting the pi over 4, so that means shift to the right. When you subtract from the x value, so you subtract from the x value like you're doing here, that means shift to the right. And the best way to do that is just take one point and track where it goes. So if we're shifting by pi over 4 units, this point should shift over to here. And that's exactly what you see. Instead of going through the origin, now it goes through pi over 4, and then you just kind of extend the behavior. And the same thing to figure out where now. So you figured out where the shape goes, but where are the asymptotes? Well, you just shift those over by pi over 4 units. So we have a asymptote here, so we're gonna it's going to shift over pi over 4 units here. And that's why we have this dotted line right here at pi over 2. It shifts over. And the same thing with the asymptote here. So it's going to shift over to the origin now in this case. So you can see it approaches the y-axis because the asymptote is going to go through the origin. It's going to go through the y-axis is just going to be the asymptote. All right. So I guess we'll just go through this and then I'm gonna stop for a second and then we'll pick up in the next section. All right, so we're gonna graph this function. So um we need to actually factor this 3 out because it doesn't actually immediately tell us what the period is gonna be. We need it to be 3 times, like we need it to be of this form right here. So notice there's a factor on the outside and it's just x inside. So we don't have just x here, we have 3x. So what we need to do is factor out the 3. So when you do that, when you factor out 3 from this expression, you get the x, and then pi over 4 is going to become pi over 12, right? And to see why that's the case, just distribute the 3 back through. You get your 3x, and then you get 3 pi over 12, but the 4 cancel. There's a factor of 3 and 12 to give, and that cancels the 3 in the numerator to give you 4. So that's why that's why it factors in that way. And now you can see that this 3 is going to help us determine the period, right? So the period of this function right here is going to be pi over k, but k in this case is 3, so it's going to be pi over 3. So an appropriate interval to graph over is, since we're doing the cotangent and not the tangent, is going to be 0 to pi over 3. Oops. All right, so but now we're not just looking at cotangent of 3x. We're looking at cotangent of 3x minus pi over 4. So we also need, so that's going to correspond to shifting to the right pi over 4 units. So what we want to do also is, sorry, um, no, we're shifting. I got this backwards. We want to look at the factored form. So we want to look at this factored form. We're shifting over pi over 12 units. So we want to take this interval right here. So we're shifting the whole graph. So we got to shift the interval on which we're plotting our function, right? So we take this interval right here, and we're going to shift the interval by pi over 12 units. So we add 0. We add pi over 12 to the 0, and then we add pi over 12 to the 3 pi, and it gives us this interval. So we're going to graph over that interval. So it's kind of annoying. I would not give you anything this horrible if I were to give you something. I don't think it would, especially, well, let's say on an exam, I would never give you something like this. This would be really complicated. But if working through the example, hopefully it's somewhat clear. And if you don't fully understand it, just, um, you know, work, give it some time, stop the video, go do something else, and then maybe back it up or work through the example on your own. So just in summary, we can get the graph, we can get one period of the graph of the cotangent on this interval right here, and then it's going to repeat. So let's find our interval, pi over 12. So pi over 12 is right here, and then 5 pi over 12 is right here. So we're going to plot it over that. And now since we shifted, so let's look at the graph of this cotangent right here. So cotangent goes through the point pi over 2, right? And so we're shifting by pi over 12. So if I doing these calculations right, it should go through so this will be 6 pi over 12. So it should be 7 pi over 12. It should go, when you shift that point over pi over 12 units, it should go to 7 pi over 12. And it does right there, see? So it went from going through pi over 2, which is not on here actually. I guess it would be like right here, pi over 2. It's a little bit bigger than pi over 4. So this is pi over 2, I guess, and it shifted over to here. So the original graph went through that point right there. All right, I'm going to stop for a moment. Okay, so let me share my screen. All right, so this next section is on section 5.5, and this is on inverse trigonometric functions and their graphs. And at first, this title, particularly this part right here, this inverse part, might perplex you a bit because if knowing the graphs of these trig functions and knowing some properties about them, for example, that they are periodic, you might say, well, how could they possibly have an inverse? Remember a function, the kind of functions we look at are they have an inverse if and only if the graph satisfies the horizontal line test. So these graphs definitely don't satisfy the horizontal line test. But remember when you talk about function being having an inverse, it's a matter of, so yes, if that is what, let me back up. If that's what your thinking was, then you're, in one sense, you're right. The functions defined on the domains that we defined, for these trig functions, yes, they are not invertible. But remember that when you talk about a function being invertible, you have to specify the rule and the domain, right? So for example, we know if I take f to be, say, real number, a function from real numbers to real numbers given by f of x is equal to x squared, this is not does not have an inverse, right? And that's because, for example, f of -1 is equal to f of 1. They evaluate to the same, so -1 and 1 are not the same, and they evaluate to the same number, 1. And you can also see it from the graph, right? The graph looks something like this. And there we go. This horizontal line intersects at 2 spots. So when you define x squared to be a function from R to R, it does not have an inverse. But if you restrict the domain to, say, 0 to infinity as a function to R, the same rule, so remember, a function is a rule together with a set or domain. The rule is x squared, then this is let's say it, I want to say it is invertible, but I'll just say it has an inverse. So if you plot that, it's just 1/2 of the parabola, because you're not plotting over here, right? You're just plotting over the positive numbers right here. So this does have an inverse, and in fact, the inverse, g inverse of x, you can verify is square root of x. And that looks something like, well, actually, let me choose a different color. Oops. So that looks, whoa. That looks something like that. And there's this diagonal line, and there are reflections of each other over the diagonal line. So to be invertible, you have to really specify the rule and the set, which will be your domain for the rule. So now if we look at these graphs, so yes, it's true. Sine of x as a function from, so sine x as a function, let's not use a variable, let's say just sine as a function from R to -1, 1 doesn't have an inverse. And you can see there's like, here's a horizontal line. It's going to intersect at infinitely many spots, right? All the way down. That's just one. There's lots of horizontal lines. But if you restrict um, to this interval right here, and they distinguish the part of the graph in red. So from here to here, this and the length of this interval right here. So this will be wait, hold on, sorry, I didn't do it quite right. We want to graph if we restrict the function from here to here on um, this interval right here, and I guess the length of this is pi. Yes, yes. Length of interval is pi. Then you notice that, so if you just restrict your graph to this portion, this red portion, then um it does, and see, so they would do the restriction over here to this interval right here. It does have an inverse. So you just basically ignore everything going over here and over here. Um, then you do have an invertible function. So what you can say is restricted. So you restrict the domain, restricted to the interval negative pi over 2 to negative pi over 2, it does have an inverse. So the inverse of sine is going to be denoted by sine inverse right here, sine -1. Um, has domain -1 to 1, and the range negative pi over 2 to pi over 2. And it's defined as follows, like this. And sometimes it's called arc sine. And so this is going to be the graph right here. So because what you do is you take this graph and you get this diagonal line. It's not that great. Let's see if I can do better. So you get this diagonal line, and you're going to reflect it over it. So you can see that this point, yeah, I'll just leave it like that. Hopefully it's clear that when you reflect the red curve over the blue line, you get this. Remember, that's how you find the graph. You reflect it over that diagonal line. Y is equal to X. So you can actually invert sine when you restrict it to this domain. So let me just over here remind you what inverse function is. So here's a definition, just in case this definition looks really unusual to you. So let f be injective. Remember, that's part of what it means to be invertible. Actually, I want to specify the domain, the range also. So this is a function from the set A to set B, be injective. So this is an injective function. Then the inverse, which exists, and that's because it's injective. Um, denoted, so the inverse denoted by f inverse is a function. What is it a function from? It's from B to A. So it's a function. So it's a function from B to A. That's not good. Notice when you want to look at the inverse of f, you swapped A and B, the sets. You swap the domain and the codomain, or domain and the range. So then the inverse denoted by f to the -1 is a function from B to A. You swap them, defined as follows. So you say that f inverse of x is equal to y if and only if um, x is equal to f of y. So this gives you like a way of determining what an inverse function does to a given input. Um, so you say, okay, I want to apply f inverse to some point x, and x is going to be in b, because f inverse is a function from b to a, and then y is going to be some point in a. Well, to figure out so you don't know what y is, but you know that f inverse sends x to y, whatever it is. But y has to be such that this equation holds. And so this gives you like a way of solving for y and finding out what y is in terms of x, and then you know what the inverse does. And so this definition right here, this definition is just an application of this definition right here. So see, we have the sine. So our sine function, we're thinking of as a function. Sine is a function from, now we're restricting the domain. So sine is usually thought of as a function from on the real numbers, but now we want to restrict it to the smaller set so that we have a function which has an inverse. So it's going to be a function from negative pi over 2 to pi over 2, and it's going to go into the set 1, 2. Or sorry, negative 1, negative 1, 1. And so now the inverse is denoted by this, and the do when to get the domain and the codomain of the inverse, you swap these sets. So now the domain of sine inverse is negative 1, 1, which is the range of sine. Okay. And so sine inverse is going to be a function from negative 1, 1 to negative pi over 2 to pi over 2. And it's defined by this formula right here, which is exactly this one right here that I wrote. Oops. And then these are the cancellation properties. Well, it's already written there. These are the cancellation properties right here. And again, this is just true more generally. In particular, we can say f of f inverse of x is equal to x, and f inverse of f of x is equal to x. Remember, these are the cancellation properties for a function and its inverse, and these are exactly, so these two relations come from these right here. So this is just we've been looking at functions and we've been looking at inverse of functions, so this is no different than what we've been doing. So for example, we had certain polynomials had inverses, and so we could find the inverse function. Some rational functions had inverses. We looked at the exponential function. That was injective, so it had an inverse, and we called it the logarithm. Now we have these trig functions, and if you restrict the trig functions to a smaller set for the domain, these also have an inverse, and they're going to have basically all the same properties that you would expect an inverse function to have. All right, so let's look at evaluating. So to evaluate this, what we need to do is, so now we draw our unit circle as usual. I won't fill it all the way in. All right, that's as best I can do. And the domain of sine, I should say, is this right here. So we're looking at all the things that we can plug into sine. So we have this point up here and this point up here. This is going to be pi over 2, and that's going to correspond to negative 0, 1. And then this point down here is going to be negative pi over 2. That's going to correspond to the point 0, negative 1. So the t values that we can plug in are all in this interval right here, here, and here. Let me actually, can I get rid of that without destroying everything? Let me do a different color actually. So the t values that we're allowed to plug in come from this arc right here, including the endpoints. So you can plug the endpoints in. So now to figure out what sine does to, I know you probably just read it, but let's solve A. Let's try solving A. So we want to figure out what sine inverse is on 1/2, okay? Call it something, call it y. We don't know what y is, but whatever y is, it has to satisfy, so this equation holds if and only if sine of y is equal to 1/2, all right? So what we have is we have like a bunch of points on our circle right here, right? So we have those typical values. So we have like, let's see if I can draw some of them here, here, and then here. So this is pi over 4, this is pi over 6, and this is pi over 3. So it turns out that if you look at pi over 6, the points corresponding to it are root 3 over 2, 1/2, okay? Now look at the y coordinate is 1/2. So this suggests to us that y, so we're trying to figure out what y is. Well, y, it looks like it should be pi over 6, right? So y is equal to pi over 6 because sine of pi over 6 is equal to 1/2. So because y is equal to pi over 6, hence we can say that sine inverse of 1/2 is equal to pi over 6. So that's how you'd solve this. So it's like how we've been solving, trying to, it's similar to how we evaluated other inverse functions. Basically, like you want to plug a specific point into your inverse function, give the output a name. You don't know what it is, just call it y. Well, whatever it is, it has to satisfy this relationship, this equation. And then you can figure out what y has to be by using your unit circle, and you know all the t values are going to be in this red region, on this red arc. So you need to look at like pi over 6. This one here is pi over 4. This one is pi over 3. And then of course you have this one here, and this one here. This one's going to be negative pi over 6, negative pi over 4, and then this is going to be negative pi over 3. All right. So let's see. So for B, we want to do sine of negative pi over 2. Well, you can probably figure out actually what that's going to be based on this calculation here. So where do we get negative 1/2? Well, we get it from the negative pi over 6, right? Because to take to the point the xy coordinates corresponding to negative pi over 6 are going to be root 3 over 2, negative 1/2, right? And that's what we want right there with the 1/2. So to solve B, you could set up the same thing. So we're going to say sine inverse of negative, let's see, I'm going to fix this a little bit. Negative 1/2 is going to be y, and that's the case if and only if sine of y is equal to negative 1/2. But this suggests y should be equal to negative pi over 6 because sine of negative pi over 6 equals, whoops, let me fix that. Sine of negative pi over 6 is equal to negative 1/2. And so that means sine inverse of negative 1/2 is equal to negative pi over 6. Okay. Of course, you don't have to be, you're not going to have to go through all this logic and reasoning every time. It's good to do this a few times though, like work through a couple problems this way so that you can get used to figuring out how to evaluate um the inverse function. But what about this last one? Well, this is a sort of a trick question, and the reason why is this. Um, this because 3/2 is greater than one, as it says, this point 3/2 is not even in the domain of sine of so this doesn't so this value right here is not it's not well defined, and that's because remember sine inverse is a function from -1 to 1. So the only thing you can plug in to this function are points in this interval, and it spits out a point between negative pi over 2 to pi over 2. So be careful, like make sure you're plugging in values that are allowed. You cannot plug in 3/2 into this sine inverse function. All right. So these ones are sort of trick questions. Um, there's not really much you have to do. Like you could figure out like what is sine of pi over 3. That's gonna give you some number, and then you can figure out what sine inverse of that number is. Or you can just use the cancellation properties, as I say, because you're composing sine inverse with sine of pi over 3. Um, Same thing with this other one. You're doing the opposite order. You're doing sine inverse with sine, sine inverse with sine. So you just use the cancellation property, so it simplifies your life quite a bit. Um, but again, you could go through the calculations in the way that I did. Um, and then here, I guess is a good thing to note. This works. This cancellation property works only if x is between these points. Because remember, because of the sine function, we restricted the domain to this set right here. So you can only plug those values in for x. So you gotta be careful. All right, so what about cosine inverse? Well, it's basically the same thing. Um, cosine defined on the whole real line does not have an inverse, and that's because here's a horizontal line that intersects at more than one spot, and in fact, it intersects at infinitely many spots. But if you restrict the domain from 0 to pi, and then just eliminate the blue graph, then you do get um, an invertible function. You get this red graph right here, and this does pass the horizontal line test. So you're looking at cosine as a function from 0 to pi, so you restrict the domain. And this is a really important thing in mathematics, like being able to view functions on with different domains, having different domains. This is very, very common. So try to get used to something like this. Because depending on what you're trying to do, for different applications, you might need to consider a function or a rule on defined on a different set. So this is a function from 0 to pi to -1, 1. So that means cosine inverse. What is the domain and the range? Well, you just swap, right? And again, you get this definition right here just literally follows from the way inverse functions are defined. Yeah, whatever. I can't get it. Okay. And you're gonna have the same cancellation properties right here. All right, so what does the graph look like? There's the graph, and that's because when you take this graph right here, so let's do different color, I guess. I don't know. You take this diagonal line and you reflect it over at this point right here is gonna like move to a point like right here. Hopefully that's not confusing. It's a good idea to just keep track of where points go though. So this point right here gets, when you do the reflection, it gets like sent to here, and then it kind of goes down like that. And that's exactly what we have right here. So there's the point was that's the green point, and the green point like started somewhere down here, and then you reflect it over this line right here. So this point, I didn't want to do it that like that. I wanted dotted lines. So this point gets moved to there. Okay. And you, as I said, you get the same cancellation property. So let's look at an example here. So let's do example A. So we want to find cosine inverse of, let's not use parentheses, of root 3 over 2. So let's call it y, and whatever y is, it has to satisfy this equation right here. I should know, actually, let me note something first. So, um, so now we're thinking about cosine as a function from 0 to pi to -1, 1. And what does that mean in terms of the unit circle? That's terrible. That's the best I can do. So -pi, 0 to pi corresponds to this point and this point, and the t values that were allowed correspond to points in on this red arc. So we need to look at, like, if I to solve A, I need to find like arc lengths or angles in on this red bar, this red arc right here. So, oh, all right, let's do that over here. So we got this red arc is like our allowed values right here. I get this point here, and then here, and um, this corresponds to 0, and this corresponds to pi. All right, so let's try solving A. Um, so we want to do cosine inverse of root 3 or 2, call that y, and whatever y is, it has to satisfy this equation. Okay, so this is saying like we're talking about a point on this red arc where the x coordinate is root 3 over 2, so it's positive. So that means we're some point in the first quadrant. So, we got these three main angles right here, or arc lengths. And it turns out that we're going to want this point right here. This is pi over 6. And recall the coordinates to this are root 3 over 2. Let's see if I can make this a little bit thinner, the pen. So root 3 over 2, 1/2. So you can see that y has to be pi over 6. So y is equal to pi over, oops, is equal to pi over 6, because when you take cosine of pi over 6, you go to this point and you look at the x coordinate. Well, the x coordinate is root 3 over 2. So that implies that cosine inverse of root 3 over 2 is equal to pi over 6. All right, so for B, that one's kind of easy actually. This is like one of the easier ones. We want to do cosine of 0. Well, so in other words, like we're talking about an x coordinate being 0, and we want to know what's the associated arc length. Well, that one's easy to determine. It's this point right here. This is pi over 2. and the corresponding point is 0, 1. So we can see that cosine inverse of 0 is going to be pi over 2. And that's because when you take cosine of pi over 2, you get 0. So notice the connections between it. There's like we're swapping things around essentially. Let's see. Okay, so now this last one, negative pi, negative 1/2. So we're talking about an x coordinate that's negative 1/2. So that means we're in the second quadrant, as that's where the x values are negative. So we got our 3 points. Um, but actually, I don't even need to draw them. All I need to know are what are the quadrants of, what are the coordinates of pi over 6, pi over 4, and this one right here. I'm gonna get rid of the pi over 2 because I don't need it any longer. But this one right here is gonna be pi over 3. And if you consult your unit circle, which you should definitely remember, it's gonna be 1/2 um 1/2 root 3 over 2. And notice it's like notice the relationship between these. Pi over 6 is root 3 over 2, 1/2. Pi over 3 is just those points swapped. So the unit circle looks daunting at first, but there's really not a whole lot you need to remember from it. If you just remember a few points, you got the whole circle. Now, notice for pi over 3, our x coordinate is 1/2. That's close, but we want negative 1/2. So we need to take like this complementary angle um over here to get the x coordinate negative. All right, so this angle is going to be, well, so it's angle or arc length. So what is the angle or arc length measure for this? Well, we go all the way to pi over 2, and then we're in the second quadrant. We don't go all the way down to pi. So we go a little bit less. What do we go? We go uh pi minus pi over 2. So this point right here is 2 pi over 3, and the coordinates of it are negative 1/2 root 3 over 2. So at this point right here is 2 pi over 3, negative 1/2. So what that means then is that this right here, cosine inverse of negative 1/2, is going to be equal to 2 pi over 3. And that's because cosine of 2 pi over 3 is negative 1/2. Okay. All right. So um, now we're going to look at restricting the domain of the tangent function to get something that's one-to-one and hence has an inverse. So we have it's the same setup. So now we have tangent. So we're going to look at tangent as a function from the set 1/2 negative, sorry, negative pi over 2 to pi over 2 into the real numbers. So now this is like we're shrinking the domain of the tangent function. So if this is our domain, in our range for the tangent function, and this function is invertible, it has an inverse, then the tangent inverse is going to be a function from R, the whole set of real numbers, to this interval. All right. And again, we get the same cancellation properties. And then to get the graph, we're only looking at the graph from negative pi over 2 to pi over 2, so this red arc, and then we're going to reflect it over that line. So something like this. And when you reflect it over this diagonal line, you get this right here. So this is tan inverse right here, this graph. This is actually a really important function. It's interesting, like to to like learn advanced mathematics, but then go back and teach these more like fundamental classes, like on pre-calculus and calculus, because now you can like reinterpret these results and know what they say. So basically, when you get to more advanced mathematics, this will basically show there's this branch of math called topology, and it's essentially like rubber sheet geometry. So you want to classify spaces up to this notion where you can like take the space and like stretch it and twist it and bend it in different ways. And if you can do that, then you say that the two spaces are homeomorphic. So what this shows, because we have this function right here, tan inverse, this shows that the whole set of real lines is homeomorphic to this interval right here. In other words, like you can squash the real line, and these two sets are basically the same. There's another since we're talking about topology, let me pull this up. Where is this at? It's not. Um, so let me see. Coffee mug, topology. There's another thing in topology. There's this coffee mug. So to a topologist, um, so the joke is that so here's this coffee mug, and you can basically it's not a gift though. Oh, here it is. These two shapes, the coffee mug and the donut, the torus, are topologically the same because you can perform these continuous deformations. So you'd say that the coffee mug shape and the torus, that is the donut, are homeomorphic in this way. And this gives you an illustration of the homeomorphism where you can do this deformation, this continuous deformation and transformation to get from you can do it and you can do it invertible. It's invertible. That's the point of a homeomorphism is that that's why we talk about these invertible functions having an inverse because that means you can transform the space into another space, and then if it's invertible, that means you can go backwards. So of course, you don't have to understand any of this at all. It's just interesting from my perspective to go back and like learn some of this stuff and realize what does this stuff say in a deeper way. So this is a visualization of the homeomorphism between a torus and a coffee mug shape. Of course, writing the formula down, I don't even know what it looks like. It's probably really difficult to write down, but you can definitely write it down. And in this same way right here, the tangent function is a homeomorphism from the real line to this interval right here. So it says that they're a lot alike in a sense. Like, in other words, you can take any finite interval and stretch it infinitely far out as you want. And this tells you how to do it this way. Anyways, so here's the graph of the tangent on this domain, this restricted domain. And then here's the graph of the inverse. And you want to find some values. So now because we're restricting between pi and 2 pi, let's draw our unit circle to figure out like what does that mean in terms of the unit circle. So we got the unit circle, and here's pi. Now, what actually I'm going to do is not draw a solid circle because notice this is not less than or equal to, right? It's strictly less than. So we have, let me see if I can do it like that. Okay. So we have an open circle right here. And then on an open circle, this is terrible. Let's start over. It's going to be terrible anyways, but I just didn't like the way that came out. That's probably the best circle I've drawn so far. All right, so we have an open circle right here corresponding to pi over 2 because you can't plug that in. Remember, you can't plug in pi over 2 into the function, and we have an open circle corresponding to negative pi over 2. And of course, the point corresponding to it is 0, -1, and this is 0, 1. And then the allowed t values that you can plug in correspond to like everything up to the hollowed circle. But you can't plug in those circles right there. All right, so let's evaluate some. So we have 1, so we want to evaluate it at 1. So we need to draw our 3 lines. And when you take a test, the second test and the final exam, literally the first thing I would do, like go through the exam, look for where the trig problems are, and right there, the first thing you do, just draw this unit circle. So just get this unit circle in your head with these basic values, and then memorize that, and then immediately as soon as I hand you the exam, draw that unit circle by the trig problems, so you can just don't even have to worry about memorizing it when it comes time to solve those problems. You just have that unit circle there. So memorize this unit circle. Um, so this point right here is going to be well, actually, I'm going to only draw the point that we need. So it turns out that this right here is going to be pi over 4. Why is that? Well, pi over 4 corresponds to the point root 2 over 2, root 2 over 2. So, oh, so tangent inverse of 1 is going to be equal to pi over 4. And that's because when you take tangent pi over 4, why do I keep using parentheses? When you take tangent of pi over 4, what is it? Remember, it's the x coordinate divided by the y coordinate. So it's root 2 over 2 divided by root 2 over 2, and that's 1. So tan inverse sends 1 to pi over 4 because tangent sends pi over 4 to 1. All right, so now let's see. So now for this next one, you have you want to take tan inverse of root 3. Well, if you look at this point right here, this is pi over 3, and the corresponding point is 1/2 root 3 over 2. So the claim is that tan inverse of root 3 equals root 2. Why? Why is that the case? Why does this equation right here, um why does tan inverse of root 3 evaluate to pi over 2? Well, that's because when you take tan of pi over 3, it's going to be, what is tangent? It's your x coordinate, it's your y coordinate divided by your x coordinate. So it's going to be root 3 over 2 divided by 1/2. And then the 2's cancel to give you root 3. So tan inverse sends root 3 to pi over 2 because tan sends pi over 3 to root 3. All right. Let's see. Do I want to? Oops. There's not really much to do here. I'll leave this to you to read. All right. Now let me stop sharing for a moment.